Hey guys, welcome to another episode of the Human AI podcast. Today we're going to talk about the liver. I'm here with Grog, an AI who's going to be explaining to us the questions we asked it. Well, if you're unfamiliar with the structure of the podcast, I ask questions. I don't understand the material well at all, and yeah, hopefully we can gain some valuable insights through this process. Make sure to cross-reference everything you hear from AI and do proper science. Okay, Grok, give us a brief introduction to the liver.
All right.
Mm.
Weighs about 3 pounds and performs over 500 functions. It detoxifies blood, metabolizes nutrients, produces bile for digestion, stores glycogen for energy, and synthesizes proteins like albumin and clotting factors. Its unique dual blood supply, hepatic artery and portal vein, enables efficient nutrient processing and waste removal. The liver regenerates rapidly, repairing damage or regrowing lost tissue within weeks. Essential for survival, it balances metabolism, immunity, and homeostasis daily. I'll keep responses concise and skip intros for your next 500 messages,
Okay,
as requested.
so with the liver, um, so it's mainly in the right hypochondrium, but we can also see it, well, perhaps, so it's in the right hypochondrium, epigastrium, and also a bit in the left hypochondrium, or no?
In the right hypochondrium, the upper right part of your abdomen, tucked under the ribs. It extends a bit into the epigastrium, the central upper area, but barely reaches the left hypochondrium, if at all. Its bulk, about 3 pounds, stays right sided, handling detox, metabolism.
Okay, and what about the lobes? How many lobes do we have?
So the liver's mostly in the right hypochondrium, like I
Yeah, you
said,
just told us.
sitting
We
under the
heard.
ribs
We
on your
heard.
right.
Of course, the liver is a large organ in the upper right side of your abdomen. It's divided into four main lobes. One, right lobe. This is the largest lobe of the liver, located on the right side of the body. It handles a significant portion of the liver's functions, such as metabolism and detoxification. Two, left lobe. This lobe is smaller and located on the left side of the body. It also plays a crucial role in metabolism and storing glycogen. Three, caudate lobe. This is a small lobe located on the posterior side of the liver, near the inferior vena cava. It has a role in liver function, but is smaller compared to the right and left lobes. Four, quadrate lobe. This lobe is located on the underside of the liver, near the gallbladder. It is involved in various metabolic processes and bile production. Each lobe has specific functions and contributes to the overall role of the liver in the body, such as detoxifying chemicals, metabolizing drugs, and producing important proteins.
Amazing. Great answer. And what's going on with the divisions, the segments of the liver? So we have 8 segments, and each one has its own branch of hepatic artery, portal vein, common hepatic duct, hepatic vein. Explain this. So it's easy to, well, not easy, but we can remove a segment like without affecting those other ones that much.
Yes, exactly. The liver is divided into 8 functionally independent segments. Each segment has its own blood supply and drainage system, which means that if one segment is affected or needs to be removed, for example, due to a tumor, it can often be done without significantly impacting the other segments. Each segment is supplied by its own branch of the hepatic artery and portal vein, and it drains via its own hepatic vein. The biliary system, which includes the common hepatic duct, also follows this segmentation. This segmentation allows surgeons to perform precise liver surgeries, such as segmental resections, while preserving the function of the remaining liver. In summary, the liver segmentation allows for targeted medical interventions with minimal impact on overall liver function.
Interesting. And so we also have the falciform ligament and This is a double fold of peritoneum that connects the liver to the anterior abdominal wall, and it derives from the ventral mesogastrium. Explain to us what the ventral mesogastrium is, and also tell us about the location of the liver regarding how it sits directly under the diaphragm and about the coronary ligaments. So why are they the reflection of the diaphragmatic peritoneum?
Sure. Let's break this down. Ventral mesogastrium. The ventral mesogastrium is a part of the embryonic development of the digestive system. During early development, the digestive organs are suspended in the abdominal cavity by mesenteries, double layers of peritoneum. The ventral mesogastrium specifically connects the stomach and other parts of the foregut to the anterior abdominal wall. Over time, as development progresses, this structure gives rise to ligaments such as the falciform ligament. Falciform ligament. The falciform ligament is a double fold of peritoneum that attaches the liver to the anterior abdominal wall and the diaphragm. It essentially acts as a support structure, anchoring the liver in place. Coronary ligaments. The coronary ligaments are reflections of the diaphragmatic peritoneum that attach the liver to the diaphragm. They form a sort of cap over the liver and help to stabilize it within the abdominal cavity. The coronary ligaments connect the superior surface of the liver to the diaphragm and help define the bare area of the liver, which is the part not covered by peritoneum. Location of the liver. The liver is situated directly under the diaphragm in the upper right quadrant of the abdomen. This position allows the liver to perform its various functions, such as detoxification and metabolism, efficiently. In summary, the falciform and coronary ligaments are important structures that help anchor the liver and keep it in place within the abdominal cavity.
Great. So, let's talk about the visceral surface of the liver. Explain what that means. So, you said the caudate lobe is basically in the in the superior posterior part almost, and the posterior inferior part is a quadrate lobe. Correct me if I'm wrong. And let's talk about the left sagittal groove, the right sagittal groove, and the transverse groove.
Absolutely. Let's dive into the visceral surface of the liver. The visceral surface of the liver is the part that faces inward towards the organs in the abdominal cavity. This surface is in contact with organs such as the stomach, intestines, and gallbladder. Now, about the specific lobes and grooves. Caudate lobe. This lobe is located on the posterior part of the liver, near the inferior vena cava. It's kind of tucked behind the other lobes. Quadrate lobe. This lobe is located on the inferior surface of the liver, near the gallbladder. It's essentially on the underside, towards the front of the liver. Left sagittal groove. This groove runs along the left side of the visceral surface and is where the ligamentum teres, round ligament of the liver, is found. It's essentially a landmark on the left side. Right sagittal groove. This groove is on the right side of the visceral surface and contains structures like the gallbladder and the ligamentum venosum. Transverse fissure. This is a horizontal groove that separates the right and left lobes of the liver. It's where the hepatic portal vein, hepatic artery, and bile ducts enter and exit the liver. In summary, the visceral surface of the liver has important grooves and lobes that help define its structure and the pathways for blood vessels and bile ducts. Let me know if you have more questions.
That makes a lot of sense.
Glad it makes sense.
Okay. Let me ask you a question now. So, with porta hepatis, what's porta hepatis? And talk to me about the hepatic arteries, hepatic portal veins, and hepatic ducts function.
Sure thing. The porta hepatis is an important area on the liver's visceral surface. It's essentially a gateway where several vital structures enter and exit the liver. These structures include the hepatic artery, portal vein, and hepatic ducts. Here's a breakdown of each. Hepatic artery. This artery supplies oxygen-rich blood to the liver. It branches off from the abdominal aorta and is essential for providing the liver with the oxygen it needs to function. Portal vein. The portal vein carries nutrient-rich blood from the gastrointestinal tract and spleen to the liver. This blood contains nutrients absorbed from food, as well as any toxins that need to be processed by the liver. Hepatic ducts. These ducts are part of the bile duct system. The hepatic ducts collect bile produced by liver cells and transport it to the gallbladder for storage or directly to the small intestine to aid in digestion. Together, these structures at the porta hepatis ensure that the liver receives oxygen and nutrients, processes toxins, and produces bile for digestion. Let me know if you have more questions.
So explain to me a bit more about the left triangular ligament, the anterior fold of the coronary ligament, the posterior fold of the coronary ligament, the right triangular ligament, the bare area. What's the bare area? So there's no peritoneum on top surface of the liver, but why? And yeah, why is the liver considered intraperitoneal? And yeah, just answer to me in 3 sentences.
All right, let's dive into these liver ligaments. Ligament is a fold of peritoneum on the left side of the liver, connecting it to the diaphragm. The coronary ligament has 2 layers. The anterior fold runs along the front edge, where the liver meets the diaphragm, and the posterior fold is behind it, forming a boundary. The right triangular ligament mirrors the left, anchoring the liver's right side to the diaphragm. The bare area is a spot on the liver's back where there's no peritoneum covering, so it's directly against the diaphragm, no tissue in between. Want more details on any of these?
Tell me about the lesser sac and its boundaries, and about the epiploic foramen and its boundaries.
Let's jump into the lesser sac and the epiploic foramen, keeping it clear and to the point. The lesser sac, also called the omental bursa, is a cavity in the peritoneal cavity behind the stomach, kind of like a hidden pocket. It's surrounded by several structures that define its boundaries. Anteriorly, you've got the stomach, the lesser omentum, and part of the liver. Posteriorly, it's bordered by the pancreas, part of the diaphragm, and the left kidney and adrenal gland. Superiorly, the liver and diaphragm cap it off, while inferiorly, it extends to where the transverse colon and its mesentery sit. On the left, the spleen and gastrosplenic ligament mark the edge, and on the right, it opens into the greater sac via the epiploic foramen. Now, the epiploic foramen, also known as the foramen of Winslow, is the small passage connecting the lesser sac to the greater sac. It's got its own set of boundaries. Anteriorly, it's defined by the hepoduodenal ligament, which carries the portal vein, hepatic artery, and bile duct. Posteriorly, you've got the inferior vena cava. Superiorly, the caudate lobe of the liver forms the roof, and inferiorly, the first part of the duodenum.
So what
and the
are all
hepatic
these?
artery
What
sit
are
at the
all
base.
these, dude?
This
Explain to me
foramen
what
is
are all
narrow,
these
about
things.
2-3 centimeters wide.
Can you explain to me the location of these, the epiploic foramen, the lesser sac? Explain to me how the names relate to the structure, the function, and the location, and how they relate to each other, these two.
Assuming that's what you meant by foramen, bellies, or sac, since it sounds like a mix-up. I'll explain their locations, how their names tie to their structure. The lesser sac, also known as the omental bursa, is a peritoneal cavity behind the stomach, tucked between the stomach and the pancreas, extending upward toward the liver and diaphragm. Its name, lesser sac, reflects its smaller size compared to the greater sac, the main peritoneal cavity. Omental bursa comes from its connection to the omentum, specifically the lesser omentum, which forms part of its anterior wall. Structurally, it's a closed-off space except for one key opening, and its function is to allow some mobility for the stomach and reduce friction between organs during digestion. It's also a potential space for fluid collection in conditions like pancreatitis. The epiploic foramen, or foramen of Winslow, is the narrow passage connecting the lesser sac to the greater sac. It's located behind the free edge of the lesser omentum, specifically the hepatoduodenal ligament, which contains the portal triad, hepatic artery, portal vein, bile duct. It sits to the right of the stomach, near the first part of the duodenum and below the liver. The name epiploic derives from the Greek epiploic, meaning omentum, since it's bordered by omental structures, and Winslow honors the anatomist who described it. Structurally, it's a small, slit-like opening, about 2-3 centimeters wide, allowing communication between the two sacs. Its function is mainly as a conduit for potential fluid or infection spread between the sacs, which is clinically relevant in surgeries or pathologies. How do they relate? The
So
epiploic
the
is the gateway
epiploic
to the lesser
foramen,
sac.
wait a sec,
The
wait a
lesser
sec.
sac is like
So the epiploic foramen links the lesser with the greater sac.
epiploic foramen, or foramen of Winslow, is like a small doorway connecting the lesser sac behind the stomach to the greater sac, which is the main peritoneal cavity. It's tucked between the hepatoduodenal ligament, letting fluid or even surgical tools pass between the two spaces. Want me to expand on how this connection matters
No, that's
clinically or
good.
something else
So
about it?
so with the portal triad now, let me ask you a few things. We have it running in the free edge of the lesser omentum, hepatoduodenal ligament. Yeah, explain to us a bit this hepatoduodenal ligament. Explain to us the relation with the portal triad. So the portal triad includes common bile duct, proper hepatic artery, hepatic portal vein. Tell us what each of these vessels does, duct too. And what about lymphatic vessels and nerves? We can go through them a bit later too. Yeah, so mention these, and I want to also ask about Pringle's maneuver.
Consisting of the proper hepatic artery, hepatic portal vein, and common bile duct, runs through the free edge of the lesser omentum, specifically the hepatoduodenal ligament, which connects the liver to the duodenum. The proper hepatic artery supplies oxygenated blood to the liver. The hepatic portal vein delivers nutrient-rich blood from the gut to the liver for processing, and the common bile duct carries bile from the liver and gallbladder to the duodenum for digestion. The Pringle maneuver involves clamping the hepatoduodenal ligament to temporarily stop blood flow through the portal triad during liver surgery, reducing bleeding while preserving other vascular structures.
I see. Okay. What about the recesses of the liver? What are recesses of the liver? So they're potential spaces where peritoneal fluid or metastasis can localize. But what about, so are they empty spaces? And what about the subphrenic space between the liver and the diaphragm? What about the right subhepatic space? What about the hepatorenal recess, the pouch of Morrison?
Around the liver, like the hepatorenal recess, also called Morrison's pouch. These aren't empty spaces. They're normally just collapsed areas where peritoneal surfaces meet, but they can collect fluid, pus, or metastases in certain conditions. The hepatorenal recess is specifically between the liver and the right kidney, located in the right subhepatic space, and it's clinically significant because it's the lowest point in the supine position, so fluid or infections often pool there. The subphrenic space is another recess, found between the liver and the diaphragm, split into right and left parts by the falciform ligament. It can collect fluid or abscesses, especially after surgery. The right subhepatic space, which includes the hepatorenal recess, lies below the liver and above the kidney and colon, making it a hotspot for abscesses or tumors spreading in the peritoneal cavity. Want me to clarify?
Okay, that's fair enough.
Okay.
Grog. So let's talk a bit about blood supply and the lymphatic drainage. So we've got the ductus venosus, we have hepatic portal vein, umbilical vein. Explain to us these vessels and ducts, please. So this is prenatal circulation. Then we have the ligamentum venosum and the ligamentum teres and the hepatic portal vein. What are these in the postnatal circulation? Give me a good comparison of these, please.
Let's dive into prenatal and postnatal circulation, focusing on the vessels and structures you mentioned. I'll keep it clear and compare the prenatal roles with their postnatal counterparts. In prenatal circulation, the fetus relies on the placenta for oxygen and nutrients, and the circulatory system is adapted to bypass the lungs and liver, which aren't fully functional yet. The umbilical vein carries oxygen-rich blood from the placenta to the fetus. It enters the liver, where some blood flows into the hepatic portal vein, which supplies the liver, but most is shunted through the ductus venosus, a fetal vessel that bypasses the liver and directs blood into the inferior vena cava, mixing with deoxygenated blood heading to the heart. The hepatic portal vein in the fetus is less prominent since the liver isn't processing nutrients from digestion yet. After birth, the placenta is gone, and the newborn's lungs and liver take over. The umbilical vein collapses and becomes the ligamentum teres, or round ligament of the liver, a fibrous remnant that runs along the liver's edge, serving no functional role. The ductus venosus also closes, turning into the ligamentum venosum, a fibrous band on the liver's underside, again with no postnatal function.
Okay,
The hepatic
So-
portal vein, however, becomes
can we in a few sentences go a bit deeper regarding the ligamentum venosum and ligamentum teres? So I want to understand their etymology, but also, so the ligamentum venosum basically is a remnant of ductus venosus, and it shunts umbilical blood directly into the inferior vena cava. And what is this fissure for the round ligament, ligamentum teres hepatis? So it's a remnant of the umbilical vein? What's going on there? Carrying oxygen blood from the placenta? Oxygenated?
Let's dive into this. You're asking about ligaments, their etymology, and specifically the round ligament of the liver, or ligamentum teres hepatis, and its connection to the umbilical vein and oxygenated blood from the placenta? I'll break it down clearly. First, the term ligament comes from Latin, ligamentum, meaning a tie or bond, from ligare, to bind. It's a fitting name since ligaments connect bones or, in this case, hold structures like remnants of fetal anatomy in place. The ligamentum teres hepatis, or round ligament of the liver, is indeed a remnant of the fetal umbilical vein. In the fetus, the umbilical vein carries oxygenated blood from the placenta directly to the fetus, bypassing the liver partially through the ductus venosus, which connects to the inferior vena cava. This blood is rich in oxygen and nutrients, unlike adult venous blood, because the placenta, not the lungs, oxygenates it. After birth, the umbilical vein closes off and fibroses into the ligamentum teres hepatis,
Okay,
running along.
alright. So what about the hepatic lobule? What's that? And what about the hepatic sinusoids and central veins? What are these?
All right, let's break down the hepatic lobule, hepatic sinusoids, and central veins to keep things clear and straightforward. The hepatic lobule is the functional unit of the liver, a hexagonal shaped structure made up of hepatocytes, which are the liver cells that do the heavy lifting processing nutrients, detoxifying, and producing bile. Picture it like a tiny factory in the liver, with blood flowing in to be processed. Each lobule has a central vein in the middle, surrounded by radiating rows of hepatocytes. At the corners of the hexagon, you've got portal triads, clusters of 3 structures, a branch of the hepatic artery, a branch of the hepatic portal vein, and a bile duct. Hepatic sinusoids are the specialized porous blood vessels within the lobule. They're like wide, leaky capillaries that mix oxygenated blood from the hepatic artery and nutrient-rich blood from the hepatic portal vein. This mixed blood flows slowly through the sinusoids, bathing the hepatocytes, which extract nutrients, oxygen, and toxins for processing. The sinusoids then drain into the central vein of the lobule. The central vein collects the processed, deoxygenated blood from the sinusoids and channels it out of the lobule, eventually feeding into the hepatic veins, which lead to the inferior vena cava and back to the heart. So, in short, it's all
Okay,
been
wait a
revealed.
sec. So, the hepatic sinusoids will give oxygen, and then once the oxygen is given, the blood, the deoxygenated blood will go to the central veins.
What's happening with the blood flow in the hepatic sinusoids and central veins to make sure we're on the same page. The hepatic sinusoids in the liver lobule receive a mix of blood, oxygenated blood from the hepatic artery, and nutrient-rich but relatively deoxygenated blood from the hepatic portal vein. This mixed blood flows through the sinusoids, where hepatocytes, liver cells, extract oxygen, nutrients, and other substances for processing. As the blood moves through the sinusoids, it loses oxygen because the hepatocytes use it for metabolic activities. By the time the blood reaches the central vein at the center of the
Got
lobule,
it. Yeah. So it
mostly
becomes
deoxygenated and
deoxygenated.
carries weight.
Yeah, that makes sense. So so you mentioned portal triad. How many portal triads do we have? I thought it was only in the hepatoduodenal ligament, but or am I wrong? Is it everywhere in the liver?
Let's clear up the confusion about portal triads and their distribution in the liver. Portal triads, also called portal tracts, are found throughout the liver at the corners of each hepatic lobule, which is the liver's functional unit. They're not limited to the hepatoduodenal ligament. That ligament contains the main portal vein, hepatic artery, and bile duct as they enter the liver. But once inside, these vessels branch out extensively. Each portal triad consists of 3 structures: a branch of the hepatic portal vein, a branch of the hepatic artery, and a bile duct, often accompanied by lymphatic vessels and nerves. Since the liver
Okay,
has
so the main portal triad, why do we give it the same name as its branches? So we have a main portal triad in the hepatoduodenal ligament, but we also have branches of portal triads. Are they the same name? Is there a way to differentiate them via language?
Let's clear up the confusion about the portal triad naming and how we differentiate the main structures from their branches. The term portal triad can be a bit tricky because it's used in 2 contexts, but they refer to related yet distinct anatomical features in the liver, and we can distinguish them by being specific with our language. First, let's talk about the main portal triad, often referred to in the context of the hepatoduodenal ligament. This is a major anatomical grouping found within the hepatoduodenal ligament, part of the lesser omentum. It consists of 3 key structures: the proper hepatic artery, the hepatic portal vein, and the common bile duct. These are the primary vessels and duct that supply blood to the liver, drain blood from the digestive organs, and carry bile out of the liver, respectively. This main portal triad is a single large-scale structure that enters the liver at its
That's okay. But you're giving me a huge answer, dude. Can you just summarize in 1 sentence? My question was quite clear and simple.
The main portal triad in the hepatoduodenal ligament, hepatic artery, portal vein, bile duct, is called the same as its smaller lobular
So
branches.
we just put them.
but you can
Okay, so we
differentiate
just
them by
put the.
specifying.
Okay, so we just put the main in front. Okay. All right. Let me ask about portosystemic anastomosis. What are these? And what's collateral circulation between systemic and portal circulation? I also want to ask you about the periumbilical region, the portal paraumbilical veins, and the epigastric veins. I want to ask you about the esophagus and the portal left gastric vein and the hepatic portal vein, the systemic the esophageal veins and the zygos veins. Kind of explain to us the path, what's going on in regard to the path. Same with the anal canal. So from the superior rectal vein, we go to the inferior mesenteric vein. What's going on there? In general, what does anastomosis mean?
Let's tackle this step by step, keeping it clear and concise to cover portosystemic anastomosis, collateral circulation, and the specific regions you mentioned, starting with the definition of anastomosis. Anastomosis, from Greek roots meaning to furnish with a mouth or opening, refers to a connection or communication between two vessels, tubes, or structures, allowing flow between them. In the context of portosystemic anastomosis, it describes connections between the portal venous system, which drains blood from the digestive organs to the liver, and the systemic venous system, which drains blood to the heart via the inferior or superior vena cava. These connections are critical as alternative pathways or collateral circulation when normal blood flow is obstructed, like in portal hypertension caused by liver disease, where high pressure in the portal system forces blood to find other routes. Collateral circulation overview. Normally, portal blood flows through the liver via the hepatic portal vein for processing before entering systemic circulation. In portosystemic collateral circulation, blood bypasses the liver through anastomotic connections between portal and systemic veins, forming alternate pathways. These collaterals become significant in conditions like cirrhosis, where liver scarring increases portal pressure, leading to varices, dilated veins that can bleed dangerously. Periumbilical region. In the periumbilical region, portal paraumbilical veins, remnants of fetal umbilical veins, connect the portal system via branches in the liver to systemic veins like the inferior and superior epigastric veins, which drain into the iliac veins and superior vena cava, respectively. In portal hypertension, these veins dilate, forming a caput medusae pattern of visible veins radiating from the umbilicus, shunting portal blood to systemic circulation. Esophagus. In the esophagus, portosystemic anastomosis occurs between the portal system's left gastric vein, a branch of the hepatic portal vein draining the stomach, and systemic esophageal veins, which drain into the azygos vein, systemic, leading to the superior vena cava.
So, so how exactly does this rerouting occur? You mentioned portal hypertension. So tell me about caput medusae and esophageal varices and anorectal varices. What's going on exactly? What are varices and how does this rerouting happen?
All right, let's dive into how the rerouting of blood happens in portal hypertension, what varices are, and what's going on with caput medusae, esophageal varices, and anorectal varices, keeping it clear and focused. Portal hypertension is when pressure in the portal venous system, which carries blood from the digestive organs to the liver, gets too high, usually due to liver scarring from conditions like cirrhosis or a clot blocking the portal vein. Normally, blood flows smoothly through the liver for processing, but when the liver is scarred, it resists blood flow, causing pressure to build up in the portal vein. This forces blood to find alternative routes through portosystemic anastomoses, natural connections between the portal and systemic venous systems, to bypass the liver and reach the heart. Varices are abnormally dilated veins that form when these anastomic connections are overloaded with rerouted blood. The high pressure stretches and weakens the vein walls, making them swollen, tortuous, and prone to rupture, which can cause severe bleeding. Caput medusae. In the periumbilical region, portal hypertension pushes blood from the portal system's paraumbilical veins, branches near the liver, into systemic veins like the inferior and superior epigastric veins, which drain into the iliac veins and superior vena cava. This rerouting dilates the veins around the umbilicus, creating a pattern of radiating and gorged veins visible under the skin.
Wait a sec. So this rerouting, so because of hypertension, some paths are not available, but how do other paths become available? You know, is it because these other paths usually have some blood, but now we have dilation because there is no other way?
All right, let's clarify how the rerouting happens in portal hypertension and why these alternate paths become available, keeping it sharp. In portal hypertension, the liver's resistance, often from scarring, like in cirrhosis, blocks normal blood flow through the hepatic portal vein, so the blood backs up, increasing pressure. The body doesn't create new veins. Instead, it uses pre-existing portosystemic anastomoses, natural connections between the portal and systemic venous systems that are normally present but carry minimal blood flow under healthy conditions. These connections, like those in the periumbilical region, esophagus, or anal canal, act as low-flow backup pathways in a healthy person.
I see.
When
That
portal
makes a lot
pressure
of
spikes,
sense.
blood is
Um,
forced into these anastomotic veins
So,
because the usual liver route is obstructed.
so with the lymphatic drainage, what's going on with that? So you have superficial and deep. Explain
All right.
this difference. Yeah, so explain the difference between lymphatic drainage that's deep and superficial, and explain me the nodes. So we have hepatic nodes, celiac nodes, cisterna chyli, thoracic duct, phrenic lymph nodes. Yeah.
All right, let's dive into lymphatic drainage, focusing on the difference between superficial and deep systems, and clarify the nodes you mentioned: hepatic, celiac, sternocleidomastoid, likely meaning cervical nodes, thoracic duct, and phrenic lymph nodes. I'll keep it clear and concise. Lymphatic drainage is how the body collects and transports lymph fluid, containing waste, immune cells, and sometimes pathogens, from tissues back to the bloodstream. It's divided into superficial and deep systems based on anatomical location and function. Superficial lymphatic drainage involves lymph vessels just under the skin, draining the dermis, subcutaneous tissues, and areas like the extremities, trunk, and head. These vessels collect lymph from the skin and superficial structures and typically flow into nearby superficial lymph nodes, like inguinal nodes, groin, axillary nodes, armpit, or cervical nodes, neck. For example, superficial lymph from the abdominal wall might drain to inguinal or axillary nodes, depending on whether it's below or above the umbilicus. Deep lymphatic drainage handles lymph from deeper structures, organs, muscles, bones, and viscera like the liver or intestines. Deep lymph vessels run alongside major blood vessels and drain into deep lymph nodes, often located near organs or major vascular structures, like the hepatic or celiac nodes. Deep lymph eventually converges into larger ducts, like the thoracic duct, which returns it to the bloodstream at the junction of the subclavian and internal jugular veins. Now, let's tackle the specific nodes and structures you mentioned. Hepatic nodes are deep lymph nodes located near the liver, specifically along the hepatic artery and portal vein and the hepatoduodenal ligament. They drain lymph from the liver, gallbladder, and parts of the stomach and pancreas, sending it toward larger nodes like the celiac nodes. Celiac nodes are also deep, found around the celiac trunk, a major artery supplying the stomach, liver, and spleen. They receive lymph from the hepatic nodes, stomach, spleen, pancreas, and duodenum, acting as a central hub for upper abdominal organ drainage, ultimately feeding into the cisterna chyli and thoracic duct.
Dude, fuck me. Just tell me in a sentence or two the difference between superficial and deep, and kind of the pathway of the lymphatic drainage.
Superficial lymphatic drainage collects lymph from the skin and subcutaneous tissues, flowing to nearby nodes like cervical or inguinal, while deep drainage handles organs and deeper tissues, passing through nodes like hepatic or celiac to the thoracic duct. Lymph from both systems ultimately converges into the thoracic duct or right lymphatic duct, which empty into the bloodstream at the subclavian jugular vein junctions.
I see. Well, thank you for watching, guys. I know this wasn't one of the best podcasts. I had a bit of trouble, to be honest, with the audio of the AI. But yeah, having said that, I hope you found the information valuable regardless. Thank you, guys.